Welcome, everyone. We are starting something very special. The MLOps community is working on system design reviews, where we're going to be going over big data ML system architectures and doing a bit of a deep dive on what they were doing, what challenges came up, and why they architected what they architected. And today we have a very special guest. We have Shaji Kunnummel from Pinterest. I'm going to introduce him in a second. But before we dive in, we're going to record this conversation at a very high level, but moving forward, we're going to be distilling this into something that we can animate. So if you were very curious about what we're talking about, references to certain pictures, don't worry, the follow-up for this will give you a nice visualization of that. So today we're just going to have a nice and laid-back discussion with Shaji. So Shaji, welcome.
Hey, thanks, Dave. Yeah, my name is Shaji Chennan. I work at Pinterest in the content quality team. I'd been with Pinterest for a little over 1.5 years now. Prior to that, I worked at Uber for a short period of time and at Google and Yahoo for a few years.
Nice.
Yeah.
And
go
ahead.
So yeah, thanks for giving this opportunity to talk at MLOps. I've actually looked at some of your videos. I think you are actually doing a great job, kind of bridging the gap between model building and taking that to production. I had been actually working on this for like few years, taking models into production, and I know there's actually a lot of practical aspects, but not much of a theory there. I can clearly see you people are actually kind of building a theory around it, and then kind of sharing, collecting knowledge, and then start sharing that across the community. That's definitely great to see.
Oh, we really appreciate that. And let me also, while we're at it, introduce our other guest. We have Benjamin Rogojan. I always mispronounce that last part, but Ben, why don't you just say a quick hello? Tell us a little bit about yourself.
Yeah, well, first of all, thanks and hello. My name, like you said, Ben Rogojan. A quick background about me. I've worked kind of in the data science, data engineering space for probably the last 7 years, starting originally in healthcare, doing some healthcare startups, and then kind of landed myself working at Facebook in the data engineering space. And along with that, I do a lot of consulting for companies kind of across the board, whether it be, large tech companies. I've done like some pharmaceutical companies and a couple other areas, kind of just helping them manage their whole end-to-end data flows, kind of getting them to that last leg of the mile. Yeah.
Awesome. Thank you, Benjamin. And Vishnu, our always guest. Why don't you just give us a quick intro? I'm sure people are familiar with you, but say what's up.
Thanks, David. You guys have probably heard me in previous sessions, but as a real background this time, I help with operations in the MLOps community. I work at a company called Tesseract Health, where we are building an affordable portable eye imaging device, and I work on machine learning engineering there, and really love learning from the community, love learning from all of you, and really excited to get into some technical detail with David, Shaji, and Ben today.
Awesome. So thank you guys for the introduction. We're just going to get right into it. So today, the focus of this discussion is this amazing article that Pinterest put out a little while ago on detecting image similarity in near real time using Apache Flink. But before this article, they had an architecture that was essentially batch processing. And here they focus on getting that to real time or near real time. And that's what we're going to talk about today. There's a really great article, which we can reference afterwards, but we're just going to get right into the format of the system design, and let's just go right into it. So Shaji, thank you for being here. I just want to start with a high-level overview of what are Pinterest's engineering and machine learning requirements, in particular for this problem with detecting image similarity.
Yeah, good question. So Pinterest had been actually kind of historically giving a lot of focus for ML related systems, both in terms of kind of building models and using that heavily in our production system across products like home feed, related pins, search, and whatnot. But that that comes with a lot of challenges in terms of kind of productionizing systems. Especially how do we, so the building the whole kind of pipeline to build the model, take that into production, doing a lot of experimentation, and also going through the lifetime of the model itself, right? So we start with a bunch of signals. Signals actually get deprecated over a period of time. The meaning or the semantics of the signal itself changes, right? And signals are actually produced by different teams. And we, as a consumer, we actually don't have really control over like what they would actually do with the signal over a period of time. They might like deprecate one field and then introduce another field without we really knowing it, or they might actually change a score, which was actually a kind of a normalized score between 0 and 100. Now it's actually normalized score between 0 and 1, for example. So there's actually a real need to kind of build systems which actually kind of detects issues on the fly, alert on it, and if there's something goes wrong, then we should be able to kind of, the alert should be in such a way that it's actually actionable in some format. Sometimes, kind of just stop the bleeding. Sometimes like when I kind of quickly roll back to a good non-state, for example. So that's what Pinterest had been actually focusing on, like in building the whole infrastructure around it, like hosting models. How do we actually kind of even make the signals delivery in a uniform way? So that's mostly it. And along with that, we also had been building tools to kind of look into the signal. I would say, like, what exactly is this signal doing? Like, what is, can we actually explain what it is actually doing? Is there any way, let's say, someone is actually kind of opening a ticket saying that, this model or is actually doing something really bad. So what is the way to kind of, go take a deeper look at it and then try to understand what the signal is doing? Is there any kind of metadata associated with it to kind of make it easier to kind of debug it, and sometimes kind of make actions on it, right? These are like machine learning models. There is some certain accuracy and then coverage associated with that. So there will be false positives, false negatives, and then we have to deal with it in production.
Man, so it sounds like easiness of debugging, as you said in the article, is super important, and the ability to explain the signal. So I'm assuming the source, where it came from, transformations that were applied to that signal, and of course monitoring, right? You need to be able to see the health of the system in real time. I'm curious, does Pinterest have an internal system to take care of all that monitoring or in alerting, or are you using anything open source to do that?
So we do have a bunch of tools that's actually built around like some of the open sourced projects. But we do have I would say, very strong set of tools we can actually use to kind of monitor. Not only in real time, we also have monitoring tools that we can actually kind of leverage to do hourly monitoring, daily monitoring, and also do like probably like bit things like kind of look at it at like month over month, week over week analysis. So that's also pretty important, I guess. Like, as I was saying, some of the things actually get deprecated over a period of time. There is a field, someone is actually kind of using that as one of the most important signal, one of the most important feature in their model that actually gets deprecated over 6 months of period of time, right? And initially it's just like 1.1%, so no one really pays attention to it. But then over a period of time, like when it actually goes from kind of 100% to 0%, and it's something like kind of death by 1,000 cuts. No one really looks at it. So the kind of things we can do, like when you're kind of month over month analysis, or even quarter over quarter analysis, is actually very important.
That makes total sense. And I'm curious, how was the switch from this batch pipeline to this new pipeline? I'm sure one of the requirements was to make that as seamless as possible. What were some of the challenges that stick out to you during that transition?
Okay, so good question. So the batch pipeline had been actually running in production for a few years, and that's actually very mature system. People have actually built in a lot of optimization to it, a lot of monitoring on top of it. And then there are the other things. There's actually a lot of consumers, right? The people are actually using this in production for various purposes. So what we wanted to do is like make that switch from batch to real time as seamless as possible for our consumers. And there is other set of challenge. So there's actually a huge amount of historical data we have actually collected, right? So we need to get that into a serving system where we can actually kind of look at it and then make a decision in real time, right? So when you look at Flink, we have to set a timeout for it. So, and all the operation we do should be actually within that timeout period. And we can really have like when a kind of timeout set to like probably minutes or hours. That wouldn't make any sense. So making sure that we have all those backend systems available for kind of querying it, and then see we have all the sub signals available in some queryable format. Not only that, we also have to scale those systems. And on top of it, in batch mode, we have this added advantage that we produce snapshots, and then once the snapshot is actually produced, we have the luxury to kind of go over the whole snapshot, make sure that the data is actually consistent. You can also do like kind of day over day analysis. So for example, you produce like 10 billion records today, and then if it's actually kind of 20 billion all of a sudden, then that probably there is an issue. Typically data set actually grows in a very natural way, right? Probably 10 billion to probably 10.1 billion, for example, and so on and so forth. Then we lose that luxury when it comes to real time, right? Because in real time, there is no easy way you can actually kind of go over the whole set and then make a deduction on it, saying that, okay, oh, we are actually kind of producing an inconsistent result, or all of a sudden we have kind of something is actually going wrong with our backend systems and those kind of things. So as you are asking about like the debuggability and then the monitoring part, it actually has to be built right into the system so that we should be able to kind of catch issues as and when it happens. And not only we catch it, we also have a capability to kind of roll back to a good state as and when we actually detect it.
So it seems like a lot of what you're describing here are pretty crucial DevOps sort of responsibilities, from the standpoint of being able to engage in rollbacks, standpoint of being able to ensure a seamless transition between different deployments or different models of systems being able to work. And one of the things we talk a lot about in the community is the extent to which automation is a goal, is the extent to which automation is a reality in the DevOps processes. And I would love to understand your perspective at Pinterest. You've mentioned how there's so many different teams and there's sort of like dependencies on different systems and signals and inputs and outputs. How does the DevOps workflow for your team in the context of this project, how did it look? How did you notify the teams of the change that was coming and then do the deployments on that basis?
Really good question. I think that's a lot to do with like how the systems actually kind of mature over a period of time, right? So when we started, everything was actually manual, I would say. So we do the bootstrapping manually. That actually takes a couple of days because there's actually huge amount of historical data we collect. We also run one-off queries to kind of find out what issues are there, and that's how it started. But soon we realized that that's actually not a scalable model, right? Because bootstrapping, so what used to happen was that there are actually 3 systems we need to bootstrap, actually 4 systems we need to bootstrap. We create search indexes, we create data for our graph storage, we also create data for our other kind of the RocksDB part, where you can quickly, given an image ID, kind of quickly look up in the Rockstar DB and then get the related data. And what used to happen is that, okay, we talk to the teams and then they would agree that, okay, you can bootstrap it at like 10,000 QPS. And then that would take a couple of days to kind of bootstrap. But that repeatability aspect that's where the issue comes in, right? So initially we do that, then we go back and then find out a bug, and then we need to probably redo that. And when we start to redo it, we need to time it in such a way that all these teams actually agrees that we can actually write data at a much higher QPS. And that's actually not practically possible in many cases. For example, one of the teams would actually come back and then say that, hey, one of our cluster is actually having high QPS, high CPU issues, so we'll have to stop it. And then when we stop it, then the whole bootstrapping actually stalls, right? Then we have to wait until they actually recovers from the system. So going from that, completely rewriting that storage to find out what delta needs to be bootstrapped, that was actually our next step. And then even that, we started with manually, we wrote some scripts and then start running it manually. But then soon we realized that even that's actually not scalable, because when someone comes to office in the morning, the data has to be actually ready for them to work with that. So we automated that part as well, finding what delta that needs to be patched. And on top of it, I would say there are actually other aspects. For example, we actually don't have a CI/CD until now. That would mean that any code change we make, someone has to bring up a test workflow and then do some manual verification. But we would soon move away from that. I mean, again, it's it's like how much an engineer would know about the system before they can actually touch part of the system and then make some changes. And also, once we actually hand it over to our on-call team, how much they should actually know about the system before they can start operating on it. So moving from a completely manual mode, semi-manual, semi-automated, and moving to a completely automated, that's our goal. I don't know how much we can actually achieve it, but at least we foresee that we should be able to tell an on-call engineer that, okay, do these 3 steps or these 4 steps, and those steps are actually so easy to do that we probably wouldn't need any further automation from that point. When you talk about automation, there's actually another major aspect to the whole system. For example, let's say the system is actually running, and then inevitably at some point there'll be some bugs introduced, either through our own code change or one of the upstream actually introduced a bug. And at that point, we need to have a way to say that, okay, stop serving the bad data so that we won't actually start polluting our downstreamers, right? We actually don't have that at the moment. We can completely bring down the whole pipeline to handle it. But one of the things we had been actually looking into that, how do we actually deliver the signal we produce in a uniform way, that we actually have a single point where we can actually go and say that, okay, stop the bleeding. We know that there was actually an issue between timestamp T1 and T2. So don't serve data between T1 and T2. Instead, serve some safe default values or something which our consumers would need. And we are thinking that that's actually something we should be able to automate, or at least from an operational standpoint, someone would just go and then change a Zookeeper file or something and say that, okay, this is the period for which we don't really need to serve the data until someone forcefully take it off.
Got it. So there's clearly a lot of thought given to the trade-offs and the different approaches that your team tested throughout the engineering of the system, which I always love to hear about. It's so instructive to at least learn from other engineers, for me, how they think about what's necessary now versus what's necessary later, because a lot of what you learn as a younger developer is you learn different almost religious beliefs. So CI/CD is a must. Everybody tells you that nowadays, and in the practical context of a system that needs to be in production in a short amount of time, you need to engage in certain trade-offs, and it's very instructive to hear the kinds of decisions you had to make. A question that I had related to your previous answer, could you go into a little bit more detail about what you mean by the bootstrapping process and how that imposed some of the trade-offs that you talked about?
Yeah, so bootstrapping is we have actually kind of billions of entities we have already processed over a period of time in the in the batch system. In order for our system to work, we need to. It's not only for our serving purpose. We also need to have the historical data for our real-time system to work correctly. For example, so the way we actually kind of do the duplicate detection is, as and when an image is created, we actually look at our existing corpus, right? So existing corpus is our historical data. So this data needs to be actually part of our searching index. It should be part of our graph storage. Graph storage is where we actually kind of store the cluster information. So each image would be actually kind of ultimately would become part of a cluster. And there's actually a representative element of each cluster. We call them cluster heads or canonical images. And if we want to kind of start serving this data, this has to be part of all our storage systems. And also starting from at some instance, we want to kind of start processing from the real-time pipeline. So that also requires all these systems to be storage systems to be consistent, and also should have the complete and correct data.
That makes sense. And I want to talk a little bit about like the capacity that you're dealing with. It seems like you guys are dealing with a lot of data. I was looking a little bit into the article, and it stated that the number of pins saved across Pinterest can be easily over 300 billion. The rate of image creation can vary to about 100, 200 at a peak per second. And then you have, like you were mentioning, multiple clusters. Can we just dive a little bit more into the scale of what you're dealing with?
Yeah, so we at an image level, we actually have, I would say, tens of billions of images that we need to deal with. And the rate of image creation, so that's actually not really related to the actual pin creation itself, because our system is actually agnostic of what pins are actually created. We actually deal it at a media level. Image or kind of at video level, but still the number is like, I would say at peak would be around 200 QPS we need to deal with for due to some of the decisions we have actually made in the design. We also reprocess some of the previously created images every day. So there's actually a kind of a scheduled reprocessing that happens. So we should have our system scaled up to handle that as well. And on top of it, there's actually a kind of failures that we should actually anticipate, right? So, and when that failure happens, there could be like multiple actions we could take, right? One is actually kind of we roll it back to a previous state, and then and then we know that probably past few days of data we need to reprocess along with the incoming data. So that's where the scalability aspect actually comes into picture. So though the actual rate of pin creation or a kind of image creation is like probably 100 or 200, the system should be actually kind of scaled up to handle up to like probably 1000 or 2000 QPS, so that we can give an SLA to our consumer saying that if something goes wrong, we would be able to recover from it in X number of hours, for example.
Makes sense. And I'm curious, you often hear about the different styles of architectures where you have batch and streaming alongside each other. There's Lambda, there's Kappa, and all sorts of names coming out. Am I understanding correctly that you still have this batch pipeline existing alongside the real one? Or are you storing, I guess, like in the Kappa architecture, storing everything in one place indefinitely? So like I know some people use Kafka, and just store everything there indefinitely. What's going on at the level here? Are these systems still both existing simultaneously, or have you migrated to now everything being streaming?
Yeah, so good question. So currently we have two parallel systems, one real-time and one batch. But our hope is that we should be able to kind of completely deprecate the batch one and then rely on the streaming pipeline. However, there's actually one good aspect of our system is that we can actually process events independently. So each event is actually an independent event to us. For example, there's actually a new image that has been actually uploaded to at Pinterest, right? So we can go and then process that independently. This would actually mean that what we need, let's say, if at all we need to do a complete reprocessing of our systems, what we need is just the set of all images that has been actually uploaded to Pinterest. So we don't need to have the knowledge of when this image was actually created in most of the cases. We also don't need to have any state associated with this image. That's actually not the case in many other pipelines where there's actually a strict ordering in which we need to kind of reprocess some of the systems, right? So for example, if you are dealing with customer orders or probably looking at a news feed, for example, right? So there's actually a timing aspect and also the ordering also matters there. So that's when the Kappa architecture would become really complex, and also that comes with its own challenges.
Definitely. I'd love to start talking about the different system interfaces in this design. There's a lot going on here, so we don't have to spend too much time here, but can you briefly go over some of the different entities or actors involved? For example, such as Kafka. So I know that Kafka is being used here. There's also something called the VIP embeddings generator. From your perspective, what are some of the main components that are being strung into the system?
Okay, so let me answer it by taking a step backward. So what we basically do is, as and when an image is actually created at Pinterest, we need to check if this exact image has been actually used at Pinterest before, or a similar image, close enough image, so that we can actually call it as a near dupe, has been actually uploaded at Pinterest. And in order to do that, what we basically do is we have an existing corpus, as I was actually mentioning before, and we generate embeddings for the new image that has been actually uploaded, and use the embeddings to do a custom search over the existing corpus. And during that, we actually generate candidates. And then once the candidates are generated, we have an internal process to kind of enhance the set of candidates. And once the candidates are picked, we run our machine learning model, which is actually a TensorFlow model. And that actually spits out score, a normalized score between 0 and 1. And then there's a threshold we use to kind of pick up the right cluster for the newly created image. So if you look at the architecture diagram, so there's actually a VIP team. They actually handle all the media that has been uploaded into Pinterest. So they generate embeddings for us, and then once they generate embeddings, they actually kind of send notification through Kafka, and we listen to them. And for historical reasons, we actually require multiple embeddings to work with the system. So once we get the notification on embeddings, we do a stream join to reduce further downstream processing. Typically, this is actually kind of embeddings are available within like a few seconds apart. Once the embeddings are available and then we get a notification on it, we know that all the dependent signals are actually available now at this point. So that's the starting point for our processing. And then we basically extract the embeddings, send that to the our custom search engine, which is actually hosted on a system called Manas. And once the search results are actually arrived, we also do some kind of enhancing and enlarge that set of candidates. So typically we fetch 200 to 300 results from our custom search engine, and then do a 10x enhancement of it. So typically what we are dealing with is like probably around 2,000 candidates at any point. And so you can easily see that how the system is actually kind of have a huge fan out problem here. And once the candidates are generated, we actually send that to our machine learning hosting service, which is called Scorpion. And for every candidate, we get a normalized score between 0 and 1. And then once we get it, we basically sort it on the score and then pick the cluster with the highest score. And if there is no cluster found, then we would just discard it, or it actually becomes its own cluster. And then subsequent images can be actually part of it, depending on how close the image is. And once the duplicate is detected, we also need to update our storage systems. One for our serving purpose, and then also for our subsequent queries. We use a version of RocksDB that is our kind of point lookup system. So any of our consumers who wants to find out, given an image, what is the canonical ID for it, they can actually come to that system and then do that lookup. We use graph storage to store our clusters. So this is like, given a canonical image or a cluster head, give me the list of all cluster members. And we also do a write to our search index back, so that the newly created image actually part of the searchable search index.
Lots of moving parts here, and I guess the heart of the system, or at the heart of the system, is Apache Flink, this Apache Flink workflow. There's a lot going on here, so maybe we can start doing a bit of a deep dive into some of these I guess steps within like this pipeline. Does that sound okay?
Yeah.
Great. So let's start at like the very beginning, right? So we have you kind of were getting at this. You have a newly created image, and then you run the following steps. So this is going from the article, right? We have to extract LSH terms from the visual embedding. So we go from, I guess, embeddings to LSH terms, which my understanding is a reduced dimension size, or it's smaller, has a smaller memory footprint. And then from there, we go into the candidate generation and then the candidate selection. Can we just talk a little bit more about what's going on at that level? I'm sure a lot of people are curious to how the tech that you're using there, some of the challenges that came up there, and we can just kind of briefly go over that before we go on to some of the different stages in the pipeline.
Yeah, sure. So once we get a notification on like for a given image, all embeddings are available, we basically kind of query back that system and then fetch all the embeddings that we actually require. So from the embedding, we have a library which we use to kind of generate the LSH terms, as you said, like in reduced dimensions, and then use that. So LSH terms are our keywords to do the custom search, right? So the custom search index is actually built on top of LSH terms. And we basically send out, so we pick X number of LSH terms, which is actually fixed for every images, and then send that to a custom search engine. So custom search engine would treat it as this is actually kind of a sentence, and then see how many overlappings are with other images within the corpus, right? So typically we pick 3 overlapping. That's the minimum requirement, and there's actually bunch of things actually going on, because the way we actually pick the LSS terms, which is actually kind of optimized for our own purpose, which actually kind of detects the duplicates with higher coverage and accuracy. And at the so as I said, there's actually a minimum number of overlaps we are required to kind of for the search engine to return our results. We also want the results to be returned in such a way that the results are actually ordered in terms of the number of overlaps we have. Right? For example, if we have overlaps of 5 and 6, for example, we want all the results that has overlapping of 6 to be returned before 5s are actually returned. So this actually puts some stress on the search engine, because it's actually a bit different from the way typical search engines are working, right? Because even if we actually miss a few results from some of the global results in a typical search engine, which is kind of acceptable, but that's actually not acceptable in our system. It's actually acceptable at a very small issues like that are actually acceptable to a very small percentage, but at a large scale, definitely that's not acceptable. So we actually prioritize or we sacrifice latency for correctness for our search engine. So search engine actually takes a few seconds before it can actually kind of return results for larger result set. So once we get the results, we also do an candidate enhancer. That's what we call. So basically, for every result we get from the search engine, to add more variability and then kind of beat the bias of our TensorFlow model itself, we kind of add some variability to it. So for every image, we also pick every image that's actually returned from the search engine. We also pick a bunch of similar images and then kind of mix it with it and then send it to our TensorFlow model. Yeah, that's what's happening within the Apache Flink workflow. This is all handled by the Flink workers themselves. And everything that's actually kind of we deal with, like when the custom search engine or kind of TensorFlow hosting, these are all like hosted as external backends that we rely on, including our storage systems. And what we also do is we were actually talking about like debuggability and kind of easiness of debuggability and then kind of explainability aspects. So one of the thing we have actually designed our schema is with every schema can also add some metadata and also some debug information to it. So most of the failures are also captured within the schema itself. So for example, we add information like how many results were actually returned by our search engine, and for every result, what was the number of overlapping we had. We also, when we do the candidate enhancing stage, we also find out like the list of candidates that has been actually picked using the enhancement process, and also why they were actually picked up, right? What was the reason why we actually picked up them? And when we send the instances to TensorFlow or evaluation, what is the result, what is the score that's actually returned by the TensorFlow model? And if there's actually an error, we also catch it so that, if there is a false positive or something that's reported, we know that we can clearly distinguish if it's because of the score issue or if it's because of a backend issue, for example. And we do, I would say, a bit of an overkill to kind of catch a lot of information, but that has definitely helped with the dev velocity initially. And we send that, the final results along with the metadata and the debug information to Kafka. And that is actually captured in an S3 bucket. And that's where we actually run our short-term monitoring, like hourly monitoring. This is obviously available for like another long-term monitoring as well.
So I thought that was so interesting, so much of the detail that you shared in terms of the amount of data that you're gathering. It's really instructive to understand, in order to preserve that level of debuggability for this image similarity, and to even understand how important it is. I mean, the amount of data you gather is often a signal of how important something is to your workflow or to your operations, and ensuring the quality of those operations, in this case, content quality. And the fact that you're collecting all of that prediction information, all of that metadata associated with the candidates and how they were selected, that's really, really fascinating. And so just to be clear here, so you go through the process of generating an embedding, finding candidates, and then generating the similarity score. That similarity score, that's an output from a TensorFlow model, right?
That's right.
Okay, and so then you take that output from the TensorFlow model, all of that metadata about candidate generation, the image itself, or the image embedding itself, and then you send that to Kafka and to your different storage and sort of serving systems.
That's right. Before sending the storage systems, we basically kind of strip off all the debug information and some of the metadata, because if there's actually an issue with some of the backends, our storage would end up storing a lot of metadata information that could actually kind of affect our serving. Okay. Because the payload could be actually huge, and then this would be actually pretty consistent once we write to our storage. So we basically strip off the metadata and some of the metadata and debug information, but we still keep it in Kafka, where we actually have a bit more flexibility in terms of how much data we can store, and then how long we can actually store it in our S3 bucket.
Yeah, that's really, it's useful to hear that you had to strip off some of that, because I was sitting here thinking that is a lot of data to have to consistently store for every single embedding or instance.
Same.
A related question that I have here is this notion of the debuggability and how that requirement came about, and sort of how meticulously your team and you have engineered to it. Could you talk a little bit about how that requirement was defined, which team or who may have defined that over the course of the company's history or over the course of this company's project?
So specifically for this project, I would say, we do have a batch counterpart. So when we actually has some, kind of coverage and, kind of accuracy numbers, which actually means that when we actually build a new system, or a real-time counterpart of it, the quick question everyone would ask is like, how is it actually doing it with batch system, right? So we need to have a way to prove ourselves that, okay, this is actually working as expected. Not only working as expected, it's actually doing pretty similar to what the batch system is doing. Naturally there is actually divergence because of the order in which we actually kind of process events and other things, but we need to make sure that if there's actually divergence between real-time and batch system, how do we actually go and explain each and every divergence, right? So when there's actually two results that's actually not matching, how do we track it back and then say that, okay, this is actually an expected divergence versus this is actually introduced because of one of our backend failed, or some of those issues. So that's why we started thinking like, how do we actually go about doing it? And then we realized that what additional metadata or kind of debug information we need to kind of start storing it in our schema, so that tracking back to the event level, or in the event which actually originated the processing, is actually easier. So we even have automated scripts, given differences between batch and real time, we can actually completely track it back to the original point and then pinpoint where exactly that divergence actually started, right? In some of the cases, we could say that there's actually a restricted. We actually restrict the number of results by the search engine, and because of when we actually kind of restrict it, there's actually the results are actually indeterministic, right? So we don't know what would be the tail end of it. So there's actually that divergence comes in. Some of the things, even we also have looked at issues, where some of the issues are actually introduced because of floating point precisions, for example, right? We do have that capability to kind of track it down and then kind of figure out issues, or when we actually compare batch versus real time. At a company level, at Pinterest, in general, explainability is actually becoming a harder question, because people have actually built a lot of models and then they're actually used in production, and models are actually built on top of other models, right? So the output of a model is actually used as an input to other models, and it's actually a huge chain of models that's been actually built. And if there's an issue that actually comes up, not even actually a production issue, but if someone just needs to find out, like pick a field in a thrift and then find out how this is actually generated, right? That's actually a huge challenge. We ourselves actually faced that, because people, when someone actually uses output of a model to another model, they would actually just rename that model, that field, so that not even a code search can actually figure it out. So what I was actually trying to say that explainability becomes a huge part of the whole machine learning infrastructure, and also the ability to deal with short-term and then kind of long-term failures also becomes important. Does that kind of answer your question?
Yeah, absolutely. No, that was it. That was a masterclass. Thank you.
And I want to end on the storage and the serving part. So I'm going to let Benjamin lead that question as a data engineer here. So Ben, why don't you take it away?
Yeah, no, I'm just kind of curious, like how you kind of are managing all the various components in terms of backend storage for an analytical standpoint. Also, again, you've got all this real time kind of going around. So it's how do you make sure all that data kind of stays in sync? For one, I think you kind of brought that up with the batch ETL versus streaming. You brought up the whole fact you can bring back to one point. How do you deal with all those challenges and try and make sure everything stays in sync throughout this whole process?
Good question. So we actually use, as I said, we basically rely on three different storage systems. One is actually a RocksDB, which is used for low latency lookups. The other one is graph storage system, which actually provides us pagination support. For example, some of the clusters are actually pretty huge that it's not easy to get the list of cluster members in a single call. So that's the reason why we switched to using graph storage, which actually supports pagination natively. The other storage system we rely on is the Manas index itself, the search storage. And as you can see, these systems have their own consistency model, and they actually catch up with their own replication at their own cadence. But typically these systems are provides us pretty good consistency guarantees, which actually works with our systems pretty well. However, we have at times we have actually seen when the systems actually go out of sync, and then we have hourly and daily jobs, which actually just looks at our final results and then see some of the inconsistencies are actually kind of introduced because our underlying storage is actually going out of sync. And we also have scripts to kind of patch the differences when that actually happens. Typically very minor, of millions, probably like 10 or 15 records actually goes out of sync, which is most of the times.
This is very little to have out of sync, from millions. So that's pretty impressive.
Yeah. So, but yeah, we still go ahead and then kind of patch it and then bring it to consistency. For our analytics purpose, we rely on two different sources. One is there's actually a short-term storage that's created from our Kafka topic itself. So we create hourly tables, and that's actually persisted for 90 days. We also have daily snapshots created from our graph storage and also our RocksDB. So that's mostly used for kind of doing a bit longer term monitoring, like kind of day over day or kind of month over month. And this snapshots also gives us an opportunity to kind of find out the delta that has actually changed from day 1 to day 2. And if there's actually something went wrong, we can actually easily quickly find out that delta and then patch our storage systems. Yeah, and on top of it, we have scheduled workflows, which actually kind of runs as either as like hourly jobs or daily jobs, and then spits out or exports metrics that we capture, like for example, the number of inconsistencies we found out, or our coverage numbers just by looking at the previous day's data, and how is it actually doing it with our historical coverage numbers and those kind of things.
Yeah. No, that's definitely impressive to have all that data kind of moving around. One, keeping it in sync, and two, being able to use so much of it, I think, in real time. So no, I'm very impressed.
Yeah, it's good to close on these data engineering questions, which I think help us understand the entirety of the system. You started off with an image, you go through the machine learning component to really identify what that similarity score is, and then figure out how to store it in a way that all the different use cases can be satisfied. Your content quality team is really doing some fantastic work, Shaji. Thank you so much for joining us. Thank you to Ben also for joining us, and thank you to David for coordinating and really helping us have what I think is one of the best technical discussions in the community that we've had in a really, really long time. Any final comments or thoughts, David, Shaji, Ben?
Yeah, just I guess there's a lot going on here, and it sounds like you guys are growing pretty fast. And like you mentioned, you're looking to improve this system. I guess let's just close on that note. Where is this system headed? What's the next year going to look like for this workflow?
Okay, good question, Dave. So as I said, so the immediate or short term or short to medium term things that's actually happening is we are going to build a CI/CD for this, so that kind of we will have much more confidence when engineers make changes and then when it hits production. The other set of things that's actually happening is that so we build this for images, but if you look at the whole architecture, it actually doesn't have anything to do with images, right? So it should be able to work with any entities. So that's actually another set of things we are actually doing, like expanding this to other media types. It doesn't really need to be a media. We could actually expand this to any kind of entity. So so Pinterest recently launched something called Idea Pins. Which is stories, like kind of a stream of images and videos someone could put in. So you can see that the system can also be adapted to kind of deal with dupes and kind of near dupes in Idea Pins, for example. And as I said, on the storage and serving side, we are unifying the way consumers are actually going to consume our system. We want to protect. So historically, consumers had been actually kind of querying our system in various modes. There's actually signal delivery service at Pinterest, and also some of them would directly go and hit the storage systems. so we are basically trying to kind of put a we want to kind of have every consumer should have an unified way of consuming the signal, so that for future migrations we can completely drive from our side. Consumers doesn't really need to know that the data is coming from graph storage versus like when some other storage, and then we should be able to kind of quickly move that one storage system to another storage system, completely handled by our team, protecting our consumers from doing this expensive migrations. And as I was also saying, like kind of how do we deal with failures, short-term failures and long-term failures, is actually another aspect we are actively looking into. The most important thing is like how do we quickly stop the bleeding, and while the repair is actually worked on the storage systems, how do we keep two things, right? How do we actually keep processing the incoming input from our Kafka streams, so that the business is actually as usual, except that there is actually a small issue. And also, how do we actually do it in a safe and consistent way that consumers doesn't have to kind of make any additional actions further, that once the issue is fixed, it's actually just forgotten.
Awesome. It sounds like you guys are going to be doing some really exciting work, focusing on generalizing this to more data types, making this more reliable and more robust, all things that we are interested in hearing. So we look forward to what you guys are going to be putting out next. Shaji, I want to thank you for the time that you spent with us today. And yeah, for the MLOps community, where can they reach out to you if they're interested in finding out more about you and the work that you are doing? Is the best place to reach out to you via LinkedIn, or yeah, what's the best place to get to you?
Yeah, so there's a you can search by my name on LinkedIn. I hope it actually shows up.
I will. I'll make sure they got it.
Yeah.
Sounds good.
So yeah, and I mean, if you have further questions, yeah, feel free to reach out to me. I will, if I don't have the answer, I'll find out someone at Pinterest to give you the right answer. And yeah, once again, thanks for the ML Ops community, and also thanks to Dave, Ben, and Vishnu for leading the amazing discussion.
Thank you so much, guys. Well, we're going to end on that note. We hope you guys have enjoyed this conversation, and we look forward to talking with you guys next time. Bye-bye, everyone.
Yeah,
Bye.
thanks. Bye.